7 Expo 2019. Visite o maior evento de tecnologia e negócios de mídia e entretenimento da América Latina. Venha conferir os lançamentos das principais marcas do Brasil e do mundo e debater o futuro do setor com influenciadores e especialistas. Explore inovações e conheça as novas tendências. 7 Expo 2019, 26 a 29 de agosto em São Paulo. Inscreva-se agora, 7expo.com.
Internet and crystal clear 4K resolution. In 2015, Advanced Digital Terrestrial Multimedia Broadcasting DTMB-A standard was endorsed and announced by ITU as the second generation digital over-the-air TV international standard. DTMB-A offers ultra-high definition. A leading Chinese engineering lab for digital TV, or DTV-NEL, is promoting a new digital terrestrial TV technology that combines a leading Chinese engineering lab for digital TV, or DTV-NEL is promoting a new digital terrestrial TV technology that combines free-to-air TV broadcasting with the internet and crystal clear 4K resolution. In 2015, Advanced Digital Terrestrial Multimedia Broadcasting DTMB-A standard was endorsed and announced by ITU as the second generation digital over-the-air TV international standard. DTMB-A offers ultra-high definition TV images to meet the needs of today's viewers and advertisers for broadband viewing and mobile
live
reception.
video.
With
And then we're going to highlight
DTMB-A,
some key points. Thank you. Start already?
watching live events with a variety of content choices available, virtually everywhere within its network coverage to service its loyal viewers with most exciting contents available from on and offline sources. The transmission system sends 4K Ultra HD programs to quench your thirst for audio-visual impact and walk-in immersive sensation. DTMB-A TV broadcast standard is solidly built on the technology of LDPC, or Low Density Parity Check, and TDS OFDM, or Time Domain Synchronous Orthogonal Frequency Division Multiplexing. The technology offers better signal reception, anti-jamming, and high-speed mobile reception. DTMB-A is designed to work with internet-delivered content through either Wi-Fi or mobile networks. Viewers enjoy more streams, more choices, more channels, and more flexibility. The system hosts a variety of receiving terminals and is apt to deliver over-the-air TV to targeted tablets and smart TVs through Wi-Fi connectivity, mobile devices, vehicles, and TV sets. It gives viewers more choices, more channels, and more flexibility, and make TV available virtually anywhere, anytime. The standard complies with new technologies of video and audio compression and robust modulation corresponding to the increasing demand of TV operators. Its robust, adaptable, single-frequency network transmission penetrates thickness of the building walls to deliver TV contents to households to achieve fabulous indoor reception and wide coverage from mobile devices. DTMB-A boasts its emergency function to alert families of impending perils and provide video, text, audio, and graphic information when necessary. DTMB-A, a new generation broadcast platform that is attractive, convenient, adaptable, and futuristic.
Good afternoon, ladies and gentlemen. This is my first trip to SAP, and it's a great pleasure to be here. I've never been spoken in such a big hall, but this is first time a much rewarding experience. I would like to introduce you the digital television terrestrial broadcasting system and its advanced version. Again, I'm Jian Song from Tsinghua University. This is, if you are familiar with DTTB system, you will see that this is the first generation of International Telecommunication Union standard family. The first generation actually include a couple of things. If we look at the right side of this figure, you will see from transmit side, basically this standard, all the standards will segment those streamings into the packet. And with each packet, you will add certain redundancy depending on your application scenario. And then you either use amplitude, use the phase, or use the frequency to carry the information. So that's what it does for every standard. And after passing through the very tough transmission environment at the receive side, you will first achieve the synchronization and then do the demapping and decoding. Okay, that's pretty much the major functionalities of this standard, the first generation. Oh, okay. So from this slide, you will see with this standard, DTMB standard, what kind of data throughput you will be able to enjoy. I know that Brazil and other countries, several other countries in South America, they use 6 megahertz analog bandwidth. So if we choose the different combinations of constellation mapping, code rate, you will see the highest data throughput for this 6 megahertz bandwidth is about 25 megabits. If we use the standard definition, it can carry over 20 programs. If it's high definition, at least it can carry 3 to 4. Okay? And if you want to have a robust mobile reception, you can pretty much use this working mode to support several standard definition TV programs using your mobile phone for the mobile reception. Okay. And this standard has become the international standard in the year 2011. From this document, it shows all the technical specifications. And from this document, it's related to the network planning, including the protection ratio and also the other things. So basically, this is for the technology, this is for the implementation. And beyond that, I mean, this standard becomes the international standard in the year 2011. And after that, we have done something more, which promotes us like the advanced version of DTMB. From this block diagram, you can see, like the traditional first generation DTTB system, it has a similar path, signal processing, to make sure the signal can be eventually delivered to the end user. But instead of having single one, we have several pipelines which can handle the different programs with different quality of service independently. So basically here you can choose the code rate, for example, 0.4, with the constellation mapping of QPSK. And here you can use the higher code rate with a higher constellation to deliver the high definition TV program, so on and so forth. So with this arrangement, you will enjoy the great flexibility to support the multiple services with different quality of service requirement. And making the similar calculation, if we use 8 megahertz bandwidth as the benchmark, you will see with the different combination of code rate, constellation mapping, the maximum data throughput can be roughly 50 megabits per second. And this is the one we recommend to use. So it's about 40 megabits per second, which is well enough to support the ultra high definition TV 4K. Okay. And if you become a little bit greedy, you increase this sampling rate a little bit, the number will become 51 and over 40. Regarding to the 6 megahertz analog bandwidth, you simply multiplied every number in this block by 3/4. So basically 0.75. For example, here the number will be about 30 megabits per second. And after we have system design, we have done some lab tests. From lab tests, you can see depending on the different system parameters and under the different channels, you will have the slightly different performance. Apparently, with 6 megahertz analog bandwidth, the noise bandwidth is relatively narrow. So therefore, you will enjoy a slightly higher carry to noise ratio. Okay. And this standard also became the international standard in the year 2015. And we have written a book covering all the different standards, excluding ATSC 3.0, because it's really new. When we published this book in the year 2015, we haven't seen much technical details for ATSC 3.0. So therefore, this book only covers the first generation, 4 different standards, and the second generation with DVB-T2 and DTMB-A. It covers not only just the technical fundamentals, but also considering the implementation complexity. Other than that, in Chapter 9, we also listed all the testing procedures, all the proposed setups to make sure that it provides a comprehensive understanding of the system itself, as well as how to implement that, how to utilize that. And this is the chip of DTMB-A, the motherboard, and also the setup box. So basically, the echo chain of this standard is kind of mature, and this is the exciter. After that, we have done some trials to show that DTMB-A is capable to carry the ultra high definition TV with 4K. So this is some pictures showing the mobile reception, fixed reception for the ultra high definition TV programs. By the way, in our booth, we also lively demonstrate that. Other than the lab test, other than showing that in the booth, we also have the field trial for that. So this is the TV station to be broadcasting this ultra high definition TV programs. So this trial was done in the southern part of China, a city called Jiaxing, which is next to or very close to Shanghai. Does anybody ever visit Shanghai before? Okay, quite a few. But you're welcome to see the actual performance of that. So the tower is 120 meter high with this transmitter around 110 meter. And the transmit power is about 1 kilo. From this measurement, you can see it can fully support the ultra high definition TV with the frame rate of 6 frames per second. And again, the coverage, depending on the different directions, if you have favorable conditions, the maximum transmit distance is about 40 kilometers. And the shortest one is about 23. So by considering the different terrain factors, you will have quite good coverage. And this is some measurement. This is for the outdoor reception with the 10 meter high antenna, fixed reception. This is for the fixed reception for the indoor coverage. We also support a report to ITU. Together with Japanese report, we come up with a report attached to the chairman's report to our March meeting this year. Not only just for the demonstration of ultra high definition by a single transmitter, we also done something to support the single frequency network. This thing was done in Hong Kong. You see, this is the setup for the. From these slides, you can see this is the allocation of the 3 transmitters in Hong Kong. Temple Heaven is the main transmitter. The other 2 are the smaller one. With the lower power, the distance between those are over 6-7 kilometers away. And, From these slides, even though it's kind of blurred, you can see there is a strong path from this Temple Heaven, and there's 2 different paths, artificial multipath, from these 2 transmitters. And this is a received constellation mapping. The test is still ongoing. I just received the report early this morning, so I attached that for your review. This is for the fixed reception with this highest possible constellation mapping. So you will see the carrier to noise ratio, depending on the different propagation environment, is relatively good. And also this is the minimum signal sensitivities. The mobile test on this standard is also done. So you can see along this road, the test shows in green dot means the successful reception. The red one means failed, while the yellow one means critical. It's kind of unstable. But in general, you will see this one is relatively good. So that's pretty much covers the 2 standards. One is the first generation called DTMB, and it's an advanced version of DTMB-A. So you can, hopefully, after this brief introduction, you have a clear understanding that this standard can be fully able to support, will be fully able to support the ultra high definition TV, even with a single frequency network setup. And also, I'm going to talk just a little bit about the super Wi-Fi. This is a technology which could be potentially good to provide the broadband service together with the broadcasting. If we can identify certain TV white space, this technology is good for that. So this technology called super Wi-Fi is based on Wi-Fi. So that's why this one is the roadmap of the Wi-Fi. So by 2012, you will see this AO211AF, which is mature enough to support the super Wi-Fi services or the broadband service for the TV white space. It's too much. Well, I don't know what happened. It might be some version problem, but basically, the advantage is because right now, all the TV channels are fixed allocated to the different service providers. But it not necessarily mean every transmitter will transmit the same signal throughout the whole day. So therefore, it might exist so-called the TV white hole. That provides opportunity for the service provider by optimistically take advantage of this black hole and to deliver the broadband service. So that's the idea. the advantage of using the super Wi-Fi is by downshifting the transmission frequency from 2.4 gigahertz to the UHF, VHF, you will enjoy a much less propagation attenuation. So that means a larger coverage, or translate back is a higher data throughput. So that's the whole idea of the super Wi-Fi. Okay, this is some highlight of the potential advantage by using the super Wi-Fi. And this is one of the possible setup to utilize super Wi-Fi with a low power, low tower, with a high power, high tower broadcasting network. So basically, these two networks can be combined together to provide the integrated service of broadband and broadcasting. With this integration, you will be able to enjoy the better coverage by this high power, high tower, and also the interactivity, or potentially the better coverage provided by this low power, low tower structure. And in the meantime, it's not necessarily everything goes, It's not necessarily means everything goes to the wireless. Our research people or our European colleagues from EBU, they also demonstrate that it is quite possible to use cable or other means of transmission media to deliver this broadband service, or maybe broadcasting service. Okay. So that's pretty much highlight the standard itself and the potential future utilization of the super Wi-Fi. Our research team is also doing something to eventually provide the better coverage for indoor application. For example, we can use the power cable, use the power line communication to deliver the video content. We can also use LED, which is another type of semiconductor device, to provide the coverage. In this case, the LED lights intensity varies to carry the information, but in the meantime, it is so fast, nobody is going to be affected by human eyes, so you're not going to notice that. So hopefully in the future, we'll be able to provide this product, provide this demonstration, and also share our research work. So this is really a teamwork. So I would like to thank all my colleagues from here. They work for the university as a strong team of the faculty team. And also, we have a lot of engineers. We have research students, PhD students, master students. More important, we have young kids, which might be the next generation of our research engineers. With that, I finish my presentation, and thank you so much for your attention. Thank you.